Hello everyone. Let's try to resume our class of foundation engineering. We are still on chapter number 2, in situ soil testing. And last time we talked about the dilatometer test. In this video, we are going to talk about the dynamic cone penetration and California bearing ratio test. Okay. So first, we are going to talk about the dynamic cone penetration, and then next, the CBR test, and we will see how those two are linked together. Okay, what is the link between these two tests? Okay, so let's go. The dynamic cone penetration and the California bearing ratio test. First, the dynamic cone penetration test. Okay, dynamic CPT. We have seen before CPT, but that CPT was supposed to be kind of static CPT, static cone penetration test, because that one, the cone was just pushed into the ground in a static way, using static force and constant penetration rate. Okay. However, the dynamic one is not, the cone is not pushed into the ground with static force. We'll see. This is the apparatus, and we will explain based on this photo and this thematic diagram how to perform the test, and you will see what is the difference between this dynamic cone penetration and the static one. Okay, so this dynamic cone penetration is actually very faster than the static one, and it also practical, and people use it to assess the strength of shallow soil layer. Okay, because as you can see, it's kind of small, not too much stone. So only mainly upper soil layer. For example, after earthquake, if you want to know the strength of the soil, the upper layer, you can use this kind of device. Okay, it commonly used to determine parameters for pavement design. So when you are constructing road, for example, I think you know already that the California bearing ratio is used for road mainly. And this test also helps in determination of parameter for pavement design and rehabilitation. Rehabilitation after maybe a disaster, for example, or this to determine the parameter for the subgrade of road, for example, for pavement. Okay, so this figure actually shows the apparatus, as I said, and you can see the cone here. Here you cannot see it very well, but it is here. The cone is here. Okay, and there is like this weight kind of hammer and folly, and that is what is driving the cone into the ground. Okay, this is this tool, which is here again. This is the vertical graduated rod. Okay, and this one is driving rod. This one here, and the weight, the falling height of the weight is about this millimeter. So you can lift it because it's just about 8 kilograms. So these 8 kilograms, you can take it with your hand and drop it. Okay, manually. This test is done manually. You just drop it, and the weight dropping will drive the cone into the ground. Okay, so the standard, I was saying that already, standard drop hammer. This is this hammer. Oh, yeah, this schematic view is driving the cone into the ground. Okay, you drop the cone, you lift it, so hand up to this level, and you drop it free fall, and it will penetrate. It will make the cone penetrate into the ground. And then you can measure the what we call DCP index. This is just the penetration rate. It means the penetration depth per each blow. Okay, and you can see it is measured in millimeter per blow. You drop it, each blow, what penetration you get. That will give you the DCP index. Okay, and what is interesting here, and the reason why we want to link it to the CBR, the Californian bearing ratio, is by converting this DCP index. This DCP index can be converted to the CBR value, okay, by using this equation. Okay, we will come back on this equation later, but you can see here DCPT index. Okay, so instead of doing the Californian bearing ratio, you can just do this dynamic cone penetration, and you can directly obtain the the Californian bearing ratio. Okay, so let's now talk about the Californian bearing ratio test. How does it work? What is it? How does it work? I think this one you know it already. Maybe you have been talking about this in soil mechanics, but we are going to see it here also. So this uh, this figure is presenting the test for this Californian bearing ratio. Okay, you have here soil sample. This is the apparatus actually, and you can see that this is like the Proctor mold. Okay, if you remember your Proctor test, compaction test in soil mechanics, then you know this mode already. Okay, so the soil inside will be compacted exactly like what you used to do with the Proctor compaction. Okay, then you use some weights on the soil just to mimic the in situ stress. Okay, then you can see this piston, which is from this drawing. You can see this piston will penetrate into the soil sample. Okay, this is a photo. This is just a schematic view. Okay, the piston has area of this in millimeter in 3 inches. Okay, please convert this to this. The original, the book from where I took this, it was in inches. So please convert. Conversion is sometimes not perfect. So that's why in some books, you will not maybe got this in millimeters. Okay. But anyway, this is the area of this piston. Okay. The cross-sectional area of this piston. And this piston is pushed into the soil sample to penetrate. Okay. This soil sample is from road bed or road base. Okay. Soil sample. It means after establishing your road base or the subgrade, okay, you take soil sample from that road base and you put it in this mold. Okay, as you can see here, sample contained in the mold with surcharge weight on top. The surcharge is this kind of surcharge on the top of the soil sample that will help to uh, reproduce the in situ condition, okay, of the soil. Okay, because there may be weight on the soil sample in the in situ, depending on the depth from which you obtain the sample. Okay, these are just the dimension of the soil sample. Okay, in the diameter and the height in this mold. Okay, and this is the penetration piston. So this is the CBR test. Okay, so the soil sample is first compacted, as I said, using this compaction, using the Proctor compaction method, okay, or modified Proctor, okay. So you compact the soil sample first, using, of course, the optimum water content, okay, optimum water content, using the standard Proctor test. Then it is not finished. You have to shock the sample to simulate wet condition, okay. Put the soil sample in water so that you can simulate wet condition, okay. Then you place a load, surcharge load. I already explained that also, to replicate in situ stress condition, okay, from the pavement structure, okay, before you do now the pushing penetration of the piston, okay. So the standard penetration rate is about this 2 point. In some books, you will see it is 1.25, okay? But here I converted directly this 0.05 inches, okay, to millimeters. Anyway, the penetration rate is about this, about 1.25 millimeters per second, okay? And the pressure value recorded at each 2.54 millimeter. Okay, in some books you will see 2.50. Okay, 2.50, but don't worry, it's because, as I said, when you convert this to this, you will have something like this. So anyway, the penetration, the pressure value is measured at each penetration of 2.54 millimeter. Okay, so that means you keep this penetration rate okay? And you monitor the penetration depth. After getting the curve also, you can check what is the pressure, okay? Because you can see pressure here is measured here, right? You can see this pressure, okay? You write pressure and penetration, and then you check what is the pressure corresponding to each 2.54 millimeter of penetration up to the penetration of 0.5 inches or 12.7 millimeters, okay? When you will reach this penetration, then you stop. Okay, so just for your information, you can do also this in the field. The Californian bearing ratio can be conducted directly on the field also. Okay, this is in the lab, in laboratory test. This is field test. Okay, so here is a typical result from this test, CBR test. You can see here, penetration is here. The penetration rate is not changed, okay? But the penetration depth is here, written here. You keep same penetration rate, okay? For each displacement, for each penetration, you check the corresponding pressure, okay? Or stress. Stress here it is in pound per square inches. You can convert this in kilopascal if you want, okay? And the inches also, you can convert this in millimeters if you want, okay? So, but what we want, if you remember, we have to measure the pressure at each 25, 2.5 millimeter, okay? 0.1 inches. This is 0.1 inch. We measure the pressure corresponding. 0.1 again, because 0.1 plus 0.1, it will be 0.2. Okay, the pressure corresponding, and so on. Okay, so this is the curve we are obtaining. It look like the curve of bearing capacity, load settlement curve for pile loading test, for those who know what I'm talking about. Let's keep the curve here, the result here. So now, from this curve, how do you determine the CBR value? Okay, to determine the empirical CBR parameter, the pressure value at 2.54 millimeter or 0.1 inches, which is here, 0.1 inches, maybe about this one. Okay, the pressure corresponding to that is around this pressure. Okay, maybe around 70 in this case. But anyway, the pressure value corresponding to this penetration of this soil sample is expressed as the percentage of the corresponding pressure value for a standard high quality crushed rock. What does it mean? It means you do this test on a given soil sample. Okay? But there is a standard soil, let's say rock, actually, crushed rock. Standard curve. Okay? Obtain using this high quality crushed rock. and you do the ratio between the curve obtained from your soil sample, this one, and the curve, let's say the pressure, okay, this pressure, the pressure obtained here, pressure at 0.1 inch, or if you want 2.54 millimeters. Some people will say just 2.5 millimeters. Okay, the pressure corresponding to that from your sample, so from your soil sample, is compared to the pressure this high quality crushed rock, this table. Okay, you can see that pressure here. For high quality rock, crushed rock, okay, the crushed rock, you know that, right? 0.1 inches correspond to 1,000 pound per square inches. Okay. If you want, you can convert this in kilopascal, okay? It's easy. So it means you can now get the percentage because you know the pressure corresponding for this one. For your soil sample, it is around this, around 70, okay? But this is the standard. The standard we have to compare with, okay? So the ratio obtained from the comparison at the penetration of 5.08 millimeter, it means 2 inches, this inches. If that ratio is higher, okay, this value is used as CBR. Do you understand? It means you have to check two ratios. The first one is the ratio of pressure corresponding to 0.1 inches. This pressure, for example, 70. You compare it to the pressure in this table, 0.1, same displacement in 1,000. The next, the pressure now corresponding to 0.2 inches. You go here, it will be around this value. Okay, it's lower than 150, maybe 140. You do that divided by the corresponding 0.2 inches here is 1,500. So you have two ratios now. So if the second one is larger, is higher, you will maintain that value. You will keep that value as, how to say, you will consider that value as your CBR. Okay, this is the meaning. So if you do that, maybe here in our case, let's go and do that, and you will see that 0.2 is the ratio you will obtain. It will be here maybe less than 140, around 140, let's say 140. And you divide that by the corresponding ratio here is 1,500. Okay, and don't forget that it is in percentage, so you multiply by 1,000. Sorry, by 100. Okay, so by doing that, we can see that you can easily obtain 9. Okay, please try it. Use your phone or anything calculator. You calculate this. Take this value. I think this is higher than the 0.1. Okay, because the 0.1 is around 70 divided by 1,000. will be lower than this one, 140 divided by the table. Okay, actually the result is here. Okay, so it's 135 here, 100 and not 40, yeah, less than 40 actually, 35. So the first one is 78. This is directly the result from, okay, 0.1 displacement 0.1 inches. Please convert it in millimeter if you want. It gives us 78 pound per square inches. Okay. Then you take this 78 and you divide it by the standard one, which is here 1000. Okay. That will give you this 7.8%. Okay. Here 0.2 inches, this one. You check the pressure corresponding. I was saying 140, but it's saying here 135. Okay. Yeah, because I was doing the approximation with naked eyes. Okay. But anyway, 135. Okay. Then you divide this by the standard value, which is here 0.2. Standard value is 1500. You do it by yourself, you will see that you will obtain about 9. Okay. So the highest one is 9. So we maintain this one. Okay, as it's saying, if the ratio obtained from the comparison at penetration of 0.2 inches is higher, this value is used as the CBR. Okay, so for this soil sample, the California bearing ratio is 9. Okay, let's continue. Now we are going to see what is the link. Although we have already seen the equation, what is the link between the dynamic cone penetration test index? Do you remember the index, right? Dynamic cone penetration index. It means the penetration millimeter per blow. Okay. Penetration rate, when you drop the hammer, each blow will make the cone penetrate the soil. Okay. So what is the index? The index is in millimeter per blow. How many millimeter the cone get in for each blow? Okay. So we can link that to this ratio, California bearing ratio. Okay. So this equation is used to link these two. You can see here the log of CBR is equal to A minus B multiplied by this log of this index. Okay. So this index is measured in, as I was saying, millimeter per blow. And A and B, A here and B here, these are parameters that are related to the soil, type of soil. Okay, they are changing according to the type of soil. Okay. So A and B, they must be evaluated for a given soil, for example. Okay, using calibration process. You use calibration process before the dynamic cone penetration test. Before using this dynamic cone penetration test in testing on the type of soil you have. Okay. A and B, they have to be evaluated. So if you need method, more explanation about how to calibrate A and B, please let me know. But this is the end of this, not so long. So thank you very much for your time, and see you in the next video. Next video will be about I think the the borehole share test. Okay, that will be the next video. Thank you very much for your time, and see you next time.